shotgun proteomics. So you might hear this term bandied about, and shotgun proteomics just means using bottom-up techniques in proteomics. And this is, something that's been developed for the last, 20, 30 years. People are looking at different ways of improving proteome coverage in specific organisms. And I left this link in. This is from Dr. Mosley's lab, Yates and Walsh created multidimensional protein identification technology for shotgun proteomics. And this is talking a lot about, mentioned before, that this is a sample prep purification issue. How well can you separate the different peptides as they're going into the mass spec, so that the mass spec has a better opportunity to get this full proteome coverage. Of using this, so in an untargeted quantitative proteomics approach, you have proteins that are sample theoretically with increasing protein concentration, you're more likely to identify the proteins and to have confident quantitation of the protein. And so we have a few slides coming up here about how, if your protein of interest is in the sample but in a really low concentration, you're going to have a difficulty possibly identifying it and definitely quantitating it. So if you can change the distribution of proteins in your sample or peptides in your sample to favor your protein or peptide of interest, that's something you should do before it gets to the mass spec, essentially. So for untargeted quantitative peptide proteomics, there's a number of different techniques to use. Yeah.
You probably don't have to go into that part in too much detail because it's covered in the next lecture too, the quantitation.
Oh, okay.
Yeah.
Great. So I won't go into that too much. There's a number of different techniques you can use to quantify your peptides or your proteins. And you can learn more about it. Come back to the next lecture. There's been a few different really intense proteomics papers out. And this March 2012 is looking at a number of 11 common cell lines. And just, it's the same idea as this graph, where there's some proteins that are more abundant. And across 11 cell lines, 8,500 proteins were common among them all. So you can imagine that you're going to identify and quantify those proteins most often out of a total of, for this 2012 paper, 11,731 proteins. All these high abundance proteins are present in so many cell types. And specific cell types might have something that's even more highly expressed that might be interfering with your protein of interest. There's been a more recent January 2020 paper looking at 375 cell lines, just incredible. They tried to find, they looked at RNA analysis and proteomics analysis as the quantitative proteomics of the cancer cell line. And they found that there's minimal correlation with RNA analysis, and that's something that you should definitely think of when designing your experiment. If you just do RNA, you might see changes that don't correlate to actual protein level changes in the cell. Also wanted to point out again, this overlap of proteins quantified. So this is from 11 cell lines, you had that 75%, the same proteins. And here, 375 cancer cell lines. So these are cell lines that are doing some crazy stuff, but all of them had the same 5,154 proteins identified. And after that, even just 75% of them had 8,000. So the variations between cell lines are less than the things that they have in common, if that makes sense. So to get to the things that are changing and maybe interesting, the more separation of the peptides and proteins that you can do before you introduce it to the mass spec, the better.
Which again comes back to the biochemistry. So that's technically a biochemistry challenge, the pre-separation, before we get it into the mass spectrometer. So the limitation a lot of times is actually the biochemistry more so than the mass spectrometry.
Yeah, absolutely. It's a protein purification challenge of some sort. And this final slide, this deep proteome and transcriptome mapping, is just re-emphasizing that, you know, in the mass spec, you're seeing the most abundant proteins are going to make the most peptides. Since they exist at the highest quantity, they're going to just produce so many peptides, and you're going to identify them over and over again in the mass spec. Whereas just with the 40 most abundant proteins are this, you know, 75%. And these interesting things that happen at extreme levels, we can only see them in the mass spec if we can get rid of some of the noise or background of other proteins. Some of these proteins might be changing, and some of their PTMs might be changing, and we'll be able to identify them. But the challenges in quantitation, which is, I guess, is the next lecture, exist in these lower abundant proteins. So I have a number of different resources. There's some different slides about mass spec theory, the origins of mass spec, and some MS utilities that you can use for different databases. I've also highlighted the London Proteomics Discussion Group is doing they've already have a bioRxiv paper out with the SARS-CoV-2 infected host proteomics. So what can we learn? What role can proteomics play in the current epidemic? So kind of highlighted that. It's a free, you know, online webinar that you could sign up and check out in this crazy times we have. So, and again, if you have any questions, obviously Dr. Mosley is the director of the core and leading your class. Dr. Wijaratney is giving a couple of lectures. Gui Hong is a research associate. She's been here for ages, and she's really knowledgeable about sample preparation. And I encourage you to reach out to us at all if you have questions about designing experiments where you want to do proteomics.